So this is the second day of notes for the second unit that we are going to be going through, which is the nature of light and its role in investigation in modern atom. More specifically, we're going to be focusing on electromagnetic radiation, and we need to go back and revisit a little bit about that before we jump really far in. Now, the nature of electromagnetic radiation, as you recall from physics for some of you and for honors chem for some of you, any type of radiation or waves that are not matter-based is considered to be electromagnetic radiation. So these are things like your X-rays, your microwaves, the visible light spectrum. There are a couple of ways that we measure these things. One of them is wavelength, which has the Greek symbol lambda, which is this guy right here. And as you may recall from Once Upon a Time, we measure from there to there, and that gives us the wavelength. Frequency is how many waves pass you in 1 second. So it's just counting the waves as they come by. That unit for that is the hertz, or the per second, which I'm going to write a lot like this to make my life and your life a little bit easier. And then the generic formula that we have worked with in the past was this formula here, which gives us c, which is the constant for the speed of light, times the wavelength times, or c equals the wavelength times the frequency. So to sort of revisit some of these things, we need to remember that frequency and wavelength are inversely related. So, for example, looking at sample A here, the larger the wavelength compared to B, the fewer, or the lower the frequency. So we just have to remember that wavelength is inversely proportional to frequency, and vice versa. So the bigger the wavelength, the smaller the frequency. Okay, so that's just what we need to remember. So we'll just kind of keep that in mind as we go across. You've seen this diagram before, at least in honors chem. It's the same one that we use in honors chem, so I put it in this one in AP chem just so that you're familiar with it. We have some things to keep in mind is that wavelengths on this particular table or graph are in nanometers. And remember, the conversion from nanometers to meters is 1 meter is equal to 1 billion nanometers. And then frequency is in per seconds, so, or the hertz. So that's this relationship here is going to be important for a little bit later on. In terms of working with the original formula, where we have c, which is speed of light, is equal to wavelength times frequency, you have to remember that c has a value of 3.0 times 10 to the 8 meters per second. I believe that value is given to you on your cheat sheet for the AP exam. So that's something you don't necessarily have to memorize. And in this case, the frequency is 1.50 times 10 to the 18 hertz, or per seconds. So I'm just simply going to plug things in, which is 3.00 times 10 to the 8 meters per second is equal to the wavelength, which is what we're trying to solve for, times 1.50 times 10 to the 18 hertz. So we rearrange the formula, or we basically solve for wavelength, and you should get a value somewhere in the ballpark of 2.00 times 10 to the negative 10, and that's meters. This problem asks us to have it in nanometers, so I have to convert that. 2.00 times 10 to the minus 10 meters is 1 meter is equal to 1 billion nanometers. And when I plug that in the calculator, we get something like 0.2 nanometers. So in this case, we generally are going to take our sig figs from the number in the problem, or the numbers in the problem. So this one has 3 sig figs, so my answer has to have 3 sig figs. Okay? Now, classical physics, and we learned a little bit about this, or we talked a little bit about this yesterday, says that particles and waves are two completely different things. But what we learned about in terms of the progression of the model of the atom is that at some point, people like de Broglie and Niels Bohr and Schrödinger decided that the wave and particles actually tended to behave very similarly. So, for example, when an electromagnetic radiation wave goes from one medium, air, to another medium, water, it bends or diffracts. But a particle, pebble, does the same thing. Crests will go through a small opening of a water wave and spread out. Now here's where things are a little bit different. Beams of light or beams of energy or beams of electrons will go through a slit like that, and they will spread out over time, but they spread out less. So this is where we kind of melded what we could see in the real world with what we were observing with subatomic data. So with light waves, and with water waves for that matter, when they go through two slits, double slits like this, we see some interference where the crests and the peaks will cancel each other out. And so if we were to do this with water, you would have waves and then peaks and valleys and peaks and valleys and peaks and valleys where the waves were coming together, and when they come together, they cancel each other out and become, so you'd have a wave like this and a wave like this, and they're coming together and they equal a flat spot. Well, light waves do the same thing. And the way that we determined that was by shooting light waves through two slits, and when the two waves came together on the other side, we had dark spots and light spots, and dark spots and light spots. So the light spots or bright spots were where the waves were in phase, which has meant that when the waves came together at the same rate, you got a bigger wave, so those were our bright spots, and you got a dark spot where they became flat if they came at different rates. So those are things to consider, or just kind of keep in mind as we go through this process. Other things that we need to remember about energy of electromagnetic radiation, and this is a lot of the stuff we've covered already, is when you heat up a solid object, it begins to give off visible light. That has a special term in physics called black body radiation, but your glowing coals in a fire or the incandescent light bulb filament. So you got your light bulb. That is a wonderful drawing of a light bulb, and inside you've got that piece of metal, and when you run electric current through it, that piece of metal gets super bright or super hot, and it gets really, really bright, and it gives off light waves that we can see. The problem is that we had a hard time dealing with how to explain it. So physicist Max Planck said that a hot object's radiation is emitted by the atoms contained within it. And that was an important realization because they were able to, in the past, observe this phenomena, but couldn't really figure out what was going on. So what he was really idealizing is, especially with a metal, if it got enough energy, the electrons could be ejected. And when the electrons are ejected, we can see that as visible light. So the more energy that gets put in, the more energy that they can radiate, and when they can radiate more energy, we are able to see it with our eyes. So the formula that Max Planck came up with had to do with photons. So it comes in, electromagnetic radiation comes in photons, which carry a specific amount of energy. And so when we talk about that, that allows us to see the fact that light can behave both as a wave and a particle moving in the same direction. So with that in mind, we are able to calculate the energy of electromagnetic radiation using something called Planck's constant, which is 6.626 times 10 to the negative 34 joule seconds. And what this tells us is that when you have two different energies, they have to be at least one Planck's constant apart. And any energy can have multiple Planck's constants. So what that means is that if I have two energy sources, they can't be exactly the same. They have to be at least a distance apart in terms of the energy value, the number of joules of 6.626 times 10 to the minus 34. But we can have them combined, and the issue with that is that becomes a little more complicated with the math. So we're going to talk about that. We're actually not going to cover what happens when they're combined in this class. The other thing that we need to remember about Planck's constant is because it's such a small value, it's like 6 with like 33 zeros in front of it. We don't see this with our eyes, but we are able to interpret it sometimes in the form of heat, or we can feel it in terms of intensity. So how do we work with Planck's constant? It depends on what you've been given. So in this particular problem, it asks us to calculate the energy. So we're going to be solving for energy of electromagnetic radiation that is a wavelength of 7.25 nanometers. So the things that I know for sure is I know that in order to do that, I would need to use 6.626 times 10 to the minus 34 joule seconds. And since I'm solving for energy, I also need to know my frequency, and my frequency comes from the other formula, which is, I know that it's the constant for the speed of light is 3 times 10 to the 8 meters per second. And that will give me this value. But I notice that the wavelength is given to me in nanometers, so the first thing I need to do is convert that 725 nanometers to meters. So 725 nanometers to meters, 1 meter is equal to 1 billion nanometers. So 725 divided by a billion gives me 7.25 times 10 to the minus 7 meters. So I'm going to take my 7.25 times 10 to the minus 7 meters, and I'm going to plug it into my formula, which is 3.00 times 10 to the 8 meters per second equals 7.25 times 10 to the minus 7 meters times frequency. So I solve for frequency by doing a little bit of division, and I get something like 4.14 times 10 to the minus, times 10 to the 14 per seconds, or hertz. So I'm going to take that 4.14 times 10 to the 14 per seconds, and plug that into the energy formula using Planck's constant. So energy is going to equal 6.626 times 10 to the minus 34 joule seconds times the 4.14 times 10 to the 14 per seconds. In this case, seconds cancels out, and it gives me a value of the energy in the unit of joules, which in this case is 2.74 times 10 to the negative 19 joules. So the energy of the electromagnetic radiation, in this case, of a wavelength of 725 nanometers, seems to be pretty small. But that's the type of calculation you're going to be expected to be able to do. So we're going to make it a little bit harder going forward, but there's more things we need to talk about. First of all, when something absorbs energy, two things happen. Either the amount of the electrons can be ejected from the atom, and we know that, we've seen that in last year when we talked about that in honors chemistry. So the electrons get excited, they leave the atom. When they come back down and become less excited, they give off visible light. So like I said, the electrons are moved from a lower energy level to a higher energy level, and they give off light. They also can move from one orbital to another orbital of the same type. This only happens with our D block, so our transition metal elements. So the electrons can go from, say, maybe electron configuration of like 3D4, and they'll spread themselves out amongst that D block a little bit more so that it's all single elements instead of paired up. And when the atoms connect by bonds, and this part right here is going to be kind of important for what we're going to be talking about, is that the bonds can vibrate, twist, or rock. So a single bond, the atoms will rotate around that bond. A double bond, the atoms can't rotate around the bond because it's more rigid, and the triple bond, the atoms definitely can't rotate because it's even more rigid. So when we have bonds, we can break them to cause a chemical change to occur, which is a big part of following the flow of energy in chemistry. And we can also separate intermolecular forces, like your LDF or your hydrogen bonds, or your dipole interactions, by adding energy to the system. Now, when we go through the process of breaking bonds using light energy, we're looking at photons instead of waves. So photons contain a certain amount of energy per packet of that particular particle. And when you have enough of that energy in those photons, you can actually break chemical bonds. Now, these types of reactions are important because when they occur in the atmosphere, we can create pollution. An example would be formaldehyde, which comes out of automobiles. Light energy tends to break it down, creating compounds that contribute to smog. Now, what I need you to know, or remember, or think about is that 1 mole of any substance contains 6.02 times 10 to the 23rd bonds. So if I have 1 mole of formaldehyde, I technically have 1 mole of that carbon-oxygen bond. And I have 1 mole of the carbon-hydrogen bond. And I have 1 mole of the carbon-hydrogen bond. So that's where the bonds are coming from. So how this relates to bond dissociation energy, some things that we need to keep in mind is, first of all, we are given a value in kilojoules per mole, and that's going to be something that's going to be important for us in a little bit. But in order to figure out the answer to the problem, it says, what is the maximum wavelength of a photon that can cause a carbon-bromide bond to break apart if the bond dissociation energy is 210 kilojoules per mole? So what I'm going to do is I'm going to convert that 210 kilojoules per mole into something more usable, which is joules. So 210 kilojoules in 1 mole will equal 1 mole in 1 mole equals 6.02 times 10 to the 23rd bonds. And now I need to get, so that's how I'm going to get to my bonds. And then I'm going to go and convert that to joules. So 1,000 joules is equal to 1 kilojoule. And I get something like 3.5 times 10 to the minus 19 joules. So now that 3.5 times 10 to the minus 19 joules is the energy required to break apart the bonds. So I'm going to put that here. Now, some other things that I know for sure by just looking at this particular set of formula is 6.626 times 10 to the minus 34 joule seconds. And I also know 3.0 times 10 to the 8 meters per second. But I need to figure out velocity, or I'm sorry, frequency. So, but all I know is that C is equal to 3 times 10 to the 8. So what I'm going to do is I'm going to manipulate this formula to solve for V. And I'm going to plug this here. So now when I go into my formula, I have well, let me do it this way. I have E is equal to H times C over wavelength. So I'm going to plug in the numbers that I know, which in this case is 3.5 times 10 to the minus 19 joules equals 6.626 times 10 to the minus 34 joule seconds times 3.00 times 10 to the 8 meters per second over, in this case, the wavelength, which is something that I need to eventually figure out. So first thing I'm going to do is I'm going to try to get wavelength by itself by moving the equation around. So I'm going to get wavelength times 3.5 times 10 to the minus 19 joules equals 6.626 times 10 to the minus 34 joule seconds times what's left over, which in this case is 3.00 times 10 to the 8 meters per second. To get wavelength by itself, I'm going to take the 6.626 times the 3 times 10 to the 8 divided by the energy, which in this case is 3.5 times 10 to the minus 19 joules. So when I solve that out on my calculator, I get a value of 5.7 times 10 to the negative 7 meters, which I need to convert to nanometers. So 5.7 times 10 to the minus 7 meters. 1 meter is equal to 1 billion nanometers is equal to 567 sig figs 570 nanometers. So will this yellow light have enough energy to break the bond? If we go back and look at that spectrum, I would say yes, it does. It's just on the upper side of that, but it does. Now I've got one more example that I need to get through before I set you free. Couple of things about this problem. When I ask what is the maximum strength of a bond, I need to know that I'm talking about joules per photon, which also means joules per bond, and that's important to think about in a couple of minutes. The other thing is that I see that I'm in nanometers, and I know that when I'm thinking about the variables that I know values for, 3.0 times 10 to the 8 meters, and Planck's constant is 6.626 times 10 to the negative 34 joule seconds. I'm going to need to convert this 335 nanometers to meters. So 335 nanometers to meters, a billion nanometers in 1 meter gives me 3.35 times 10 to the minus 7 meters. So I'm going to plug that in here, 3.35 times 10 to the minus 7 meters. And so now, in this case, I could combine things in terms of formula, but I think it's easier if I break this one apart. So I'm going to go ahead and take into 2 steps. The 3.00 times 10 to the 8 meters equals 3.35 times 10 to the minus 7 meters. Oops, this is meters per second. Times frequency. Solving for frequency here gives me a value of 8.96 times 10 to the 14 hertz, which I'm going to plug over here. 8.96 times 10 to the 14 hertz. I'm going to take that and plug it into my energy equation. So we know that energy is equal to 6.626 times 10 to the 20, no, not 20, times 10 to the negative 34 joule seconds times 8.96 times 10 to the 14 hertz. So when I solve this for the amount of energy required in that particular bond, I get 5.93 times 10 to the minus 19 joules per photon in that maximum amount of wavelength of light that's being present. So if that's the case, I now know that 5.93 times 10 to the minus 19 joules in 1 photon, going back to what I said above, is equal to 5.93 times 10 to the minus 19 joules in one bond. So what that now allows me to do is figure out the amount of kilojoules per mole. And this is a back calculation, which is 5.93 times 10 to the minus 19 joules per bond. And I remember from a couple of slides ago that 6.02 times 10 to the 23rd bonds are equal to 1 mole of bonds. And then I know that 1,000 joules is equal to 1 kilojoule. So when all is said and done, I plug this into my calculator, I find out that there are 357 kilojoules per mole. So that's a lot to kind of digest, and if you have questions, we can talk about it. Your homework is problem set number 1, problem set number 1 is, let's see, problem set number 1 is this guy right here, 6.2, 6.12, 6.14, 16, 21, 26, 29, and 76. It has some math in it, but it's also got some relating ideas in it. It's going to be due on Monday, Tuesday. So we'll talk about it on Tuesday, and good luck.